Okay, thank you everybody for coming to the GitHub Education session. As you know, we and SIGCSE board, we try to keep our costs down. And one way that we do it is that we have fabulous sponsors who donate a lot of money and also a lot of technical expertise. Without them, you'd be paying a lot more for your registration fees. And you wouldn't really, many of you would not be able to afford coming here. So before we even start, please let's give a round of applause for our sponsors. So I won't take up too much time. We have GitHub here to tell you, many of you have used some of their stuff, but they're going to tell you some real practical experiences they've had in the classroom that you can take back and make your own. So Dan and Paul from Rice and from Cal State are going to be here, and I leave it to Vanessa to be the MC now.
Thank you. I'm very comfortable with the title of MC. Hello, thank you for coming. My name is Vanessa. My handle is Mozzarella. I'm the GM for GitHub Education, and this is GitHub's 6th SIGCSE. It is my favorite event of the year, so we're very honored to be here. Today, I have the pleasure of welcoming two of my favorite teachers who I really admire, Paul and Dan, to talk to you about their workflows for automation. But why is automation important at all? Why are we even talking about it? What's important about it? And every teacher I've talked to, I see a lot of familiar faces in the audience. Almost every teacher I've spoken to is strapped for time and strapped for resources. That's kind of the gist of what they're asking me about is how will this save me time? And as CS teachers, there's this notion of do not repeat yourself, basically in your DNA. In one implementation with continuous integration tools, that allows teachers to deliver live feedback when they push to GitHub. And with private tests, you are able to automate your assessment as well. And I think that everyone in the audience probably already knows that, but we also have some early evidence that this teaching method improves passing rates in classrooms as well. With automated assessment, one teacher, Shane Wilson at Ulster University, he decreased the amount of time that he spent grading by 80% and increased his passing rate from 76% to 90%. So it's early days of this research. I hope to come back next year with a peer-reviewed paper about, about the impact this makes. But I thought that the early anecdotal results were worth sharing. Which leads us to the topic at hand today. Exactly how do you implement this kind of automation? And Dan and Paul have prepared detailed walkthroughs of their designs at Rice and Fullerton for you to adopt in your classroom practice. First up, we have Dr. Dan Wallach. Dan's official biography is that he is professor in the departments of computer science and electrical and computer engineering and a Rice scholar at the Baker Institute for Public Policy at Rice University in Houston, Texas. Unofficial biography is that when I started working with Dan about 2 years ago, I was struck by one thing, which is what a profound realist he was. I was pretty tickled by it, actually. He was a realist about two things. He was a realist about the domain that he teaches in. He doesn't want to teach the flavor of the day. He wants to teach concepts that have a very long shelf life. And he's also a realist about the amount of time that teachers have. And he has little tolerance for administrative friction. And as we've worked together, I've also been impressed by his empathy for other teachers. And that empathy presents itself in scripts and tools that save time, which he kindly open sources for other teachers. For example, Git takes its commit times from the clocks on student computers, and Wallach spotted a student attempting to use this to submit after a deadline. Using his Travis CI GitHub workflow, which logs the time of Travis and cannot be forged by a student, he made a tool to produce a nice table with a given student's commit times and GitHub push times. Please welcome Dr. Dan Wallach.
Thank you. Just a second while I fight with the IT here. Click. Open. All right, the tech is working. Thank you for that introduction. So I'm going to talk to you today about some work that I have done in Rice's Comp 215, which is a class titled Introduction to Software Design. I'm not here to tell you about our pedagogy, but just enough to give you a sense of a you are here on a map. Our freshmen take classes that involve coding in Python, and it's all in browser. For those of you who are whipping out your phones to take pictures, that URL will get you to the PDF of exactly what you're seeing. So you don't need to whip out your phone and take pictures of every slide. It's all on my homepage. So www.cs.rice.edu/D Wallach/SIGCSE 2019. Sorry? Sure. Yep, so PDF is online, so you don't have to take a picture of every page. Okay, so our freshman pedagogy involves all the coding happens in browser, which means that we're not putting a lot of IT load on the students. It's all handled in the cloud. Actually, my colleague Scott Rixner, wave, hi Scott, built all of that, and he's amazing. I am teaching at the sophomore level, and this is the first time that most of our students are installing coding tools on their personal laptops. So this is Java coding using the JetBrains IntelliJ system. I had 180 students last fall. I'll probably have 100. I will probably have 200 plus students next fall. The gist of it is testing, 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 testing. It's mostly functional programming, which Java makes actually possible now, data structures, etc., and it's all done solo. I'm actually contemplating switching to pair programming halfway through the semester, but that's a topic for later. And after they get through my class, then everything opens up and they can take all the different electives. But that's all I want to say about pedagogy. Instead, boy, do we use a lot of tools. I just grabbed all the logos of all the tools that I use just in my one class, and there's several more that didn't have logos that were easy to grab. And how do I decide which tool? There's so many tools. Which are the right tools? So when in doubt, copy Google and Android. That's not because I have any particular affinity for them, but to the extent that what we do follows what they're doing, that means that there's a huge amount of how do I do X on Stack Overflow? How do I hack my Gradle script to solve some problem? Hey, I get this error message. How do I work around it? As long as I'm kind of following in Google's wake, then I get the benefit of a huge flow of developers fighting with their tooling decisions. And that also means that, like, for example, if I use Gradle, they use Gradle. If I use error-prone, they use error-prone. So it's not that I especially like or hate these tools, but they're standard in the Android community, which means they're well understood. Gradle actually turns out to be pretty good. It lets me do all the installation work on the student's machine. It lets me say, grab each of these libraries, and when you run a build, run this too. It's all just scripts inside Gradle. That makes it, and then once I made the decision to go with Gradle, it was like 10 inches of extra effort, and suddenly I had continuous integration running on Travis. Error-prone is Google static analysis bug finding checking tool. Like, add 3 lines to Gradle, and now it's something that the build has to pass. So each of these things, because I stayed very close following in Google's wake, I was able to benefit from all of this tooling. And oh, by the way, I've probably filed 6 or 7 bugs against IntelliJ over the years, and it's amazing. They will typically say, fixed in the next release in less than 48 hours after I file the bug. I don't know what's in the water in St. Petersburg, Russia, but they're good. So when I first said I'm going to start using Git, the thing that had me most worried was the detached head state. There are so many peculiar corners of Git that I was like, how am I going to deal with this? How am I going to explain to a student how to deal with a merge conflict? How am I going to? Turned out it really wasn't a problem, much to my surprise. That since I start off with the students coding solo, then you're not going to have a merge conflict with yourself, mostly. And IntelliJ has a front end to Git. It's their version control system front end. And all I have to teach the students is you don't commit, you commit and push. And it's like, it's a different button. And as long as you do the commit and push button and you make that be your workflow, the students follow it and it kind of works. So at least in the beginning, no merging, no rebasing, no branching, no tags, none of that. They'll get that later on, but not in the beginning. So we're using Git as a glorified save button. And that's it. But that's just fine for a first experience. And GitHub and Travis have been astonishingly reliable. There was one GitHub outage that hit on Sunday right during our deadline, and I gave a 24-hour extension. But otherwise, compared to our earlier experience using a Subversion server on campus, that was a nightmare. All the students committing right before the deadline would bring our poor Subversion server to its knees. It was not pleasant. There are occasional issues specifically with the way GitHub Classroom handles what are called clone links, and they promise me that they've got their best boffins on the problem of fixing those issues. But anyway, it's still way, way better than what Rice IT was able to give me. Here's the rough part. Week 1, welcome to class. So I give my students a 23-page PDF, linked down there, that walks them through. There's basically 2 things you got to install. Install IntelliJ and install the Java JDK. After that, everything else, when they pull the stuff from Git, it sets up everything, it installs the libraries, it installs the indentation rules. It all just kind of works. So the week 1 assignment is barely more than hello world. See where it prints Dan Wallach? Make it print your own name instead. I mean, really, really simple. And the point of that is just to prove that they can check it out, make a change, and commit it and push it back. That's it. And with a 50-minute lab, I get all 180 students through it. There are 2 or 3 corner cases every year where somebody configured their computer in a really bizarre way. And I have to figure out that, wait, why do you have files over here that are conflicting with over there? Do you mind if I delete this mess? And so 2 or 3 out of 180 seems to be the numbers I'm seeing of computers configured by students in strange ways. So your pedagogy may be different. The way I run my class is that every week, Monday morning, here's a PDF and a repo. And that covers everything you're going to do this week. Tuesday, Wednesday, they have in-person labs. Thursday night, they have their first deadline. I'll typically make them write their unit tests first. How do you make students do tests first? Require them to be due first. Then Friday morning, I will push to their repos, and I'll add more tests. So that way, they see their tests. They can keep working if they want, but Friday morning, they get my tests, which are often more vicious than theirs. And then Sunday night, everything is due, and it starts again on Monday. So it all starts with Piazza. I love Piazza. So I post 1 PDF a week, and a student clicks on one of these, and then they get one of these, and it says, Project 5, Trees and Treeps. This week, you're going to be building balanced trees. And inside the PDF, there's a link, a GitHub Classroom clone link. So every student clicks that, and they end up looking at something like this that says, hey, do you want to accept this assignment? And notice how it tacks the username onto the end. So GitHub does this for you. So you end up with your project name - student name. And that's just the name of the Git repo that you get out. They hit accept, and then they get my repo with whatever I put in it. So what do I put in it? A bunch of stuff. First, I pre-configure a whole bunch of settings for IntelliJ. I mean, everything from you're using this indentation policy to, all sorts of IntelliJ settings. Like, please don't autocomplete to those 20 libraries that I don't care about. A million little IntelliJ settings I set once and preload for them. I'm using an autograder written by Geoff Chalin at UIUC. It grunges through all the XML output of Gradle running your unit tests and lets you assign points to them. And likewise, you write a configuration for Travis CI that will run all your unit tests in the cloud. More on that in a minute. Every GitHub project has a markdown file called readme.md, so I pre-populate it with hyperlinks so the students can click it, and then they're looking at their own code as they're committing it and pushing it. I also make every student edit the README every week. I try to be as redundant as possible. Like, I have a survey at the beginning saying, tell me your name and your email and all that, and also please put it here, because I don't trust that every student finds a way not to follow some step. So the more steps that I want to, you'd be amazed. Every week, there's always some student that still has my name in it. Like, come on, kid, really? Anyway, okay, so the students start working. In this case, they're building a recursive descent parser, and you can see that the student is doing one commit for every major rule of the parser. You know, okay, I got null to work, I got Boolean to work, I got each one to work, and we do encourage the students to commit early and often, even though in industry, some places, oh, don't do a commit until until it's like meaningful. Well, we want commits early and often. And I added actually a style point each week, and part of that is that your commit message is not bogus. Like, your commit message says something about what you did. Until I required that with a point, they would just say, you know, next! Exclamation point. I'm like, no, say something real. So Friday morning, you know, we're past the Thursday night deadline. They've written their tests. Then I push my own tests. So now the students get to see my tests and run against them. If that's something you would rather not have happen, you could do this after the deadline. You know, you could do pushes post-deadline. So then the students might see it when it's too late for them to be able to respond to it. That's up to you. I've even seen some people who will do crazy firewall rules so that way Travis will grab their tests, but the students can't. I don't mind my students seeing the tests because I want them to pass them. So, you know, this is up to you. Anyway, you might notice that I had 2 oopses here. So, you know, professors aren't perfect. I had to fix my own bugs and push them back. And you can even see that this student happened to have been working at the same time that I was fixing my own bugs. The student merged on their own. And none of this, amazingly, became tech support issues for me. All the students managed to figure out how to merge, even though I never explicitly taught it. So, yay. I don't know if this is a testament to the IntelliJ being really good or what, but I never had tech support issues involving students with the merging. I told them, hey, everybody, Friday morning I'm going to push stuff. Please don't work Friday morning from 8 to 10 a.m. when you're probably asleep anyway. And it generally wasn't a problem. Anyway, you can see that the little red X's suddenly became a green check mark for this particular student. So if you click the green check mark, suddenly GitHub is pointing you to Travis. And Travis runs your unit tests in the cloud somewhere. And you can see this, this text over here is the output of this auto grader that I'm using from Geoff Chalin. And in this particular week, the auto grader knew about 7 out of 10 points. These are just points assigned to unit tests. And the rest of them, my graders will then go look at by hand. This, compared to prior years, this radically sped up my grading process. But like, I had a student once who went and edited a unit test to make their code pass it. And one of my graders was like, hey, what am I supposed to do? I'm like, pretend like they flunked that test. Like, the student grader was like, got it. And then at the end, our university has a license for Canvas. Do I like Canvas? No, but whatever. So our graders type the grades manually into Canvas. And I need to have a grader in the loop anyway to both make sure the student didn't do something stupid like break a unit test, as well as there are some things that the grader just has to evaluate, but not too much. The workflow as an instructor is that I have one repo that has 15 branches for each of the weeks. And so what I will do for each specific week is I'll do git clone to a fresh repo, and then I'll check out the branch. Then, okay, every time I type this, I have to like be super careful. rm-rf.git. Every time I type that, I feel like I'm dirty. Like, ugh. Then git init, git add, git commit. So the thing that I push to the students is a fresh repo with no history, no branches, no nothing. I maintain a complicated repo with 18 branches. That's my problem. It's not the student's problem. And these branches generally start off in a failing state, and then when the student hits the end of the week, they'll be passing. Yeah, okay. So Travis is a continuous integration service. It just runs your unit tests in the cloud. You can make it do fancier things, but keep it simple for now. Travis also, for free, no extra effort, provides a dashboard. So in real time, I can see which students have pushed and whether they're passing or failing. So I get all this lovely data, beautifully visualized out of Travis for 0 effort. It's great. And as Vanessa mentioned to you at the beginning, I've built a bunch of my own tooling. So if you go to my personal GitHub page, github.com/Dan Wallach, you'll see that I have some fun personal projects. This is my Android Wear watch face that I built to teach myself Java a couple years ago, or rather reteach. Here's what I'm going to talk about today. So 4 different tools, and I may or may not merge these all together into some super tool at some point. But anyway, each of these is a small Python script that does something involving GitHub or Travis, and I'm going to walk you through each of them next. So here's the first one, Github Graders. So it reads in all the repos. It basically says find every single repo and then filters them for everything with a given prefix and then assigns students to graders at random. Easy, right? But that's a thing I want to do. And the output of this tool is Markdown. And how many use Piazza? Yeah, so Piazza just added Markdown support last semester. So then I cut and paste this Markdown into an instructor-only Piazza post, and now all my graders see their grading assignments with hyperlinks to the Git repos. So then the graders can click to the repos and then click to the Travis output and see the auto grader without having to download any code to their machine. So in many cases, the graders can do the grading doing nothing but clicking through the web. Graders love this. The iterate over a couple thousand repos process unfortunately takes too long. And there's a GitHub search API that is supposed to fix this, but turns out it gives me different answers every time I run it. So they're working on that. Bug has been filed. Okay. Vanessa mentioned this hack earlier. So I somehow had a student whose Git commits were out of chronological order. And I'm like, how? What? Who? Huh? And I'm like, something weird happened here. And as I dug deeper, I'm like, well, okay, I know that Git gets, the time attached to your commit just comes from the system clock. So maybe this kid played some weird games by rolling system clock forward or backward to try to fool me. Well, GitHub, not Git, GitHub has all kinds of APIs, and one of them is called the Events API. So I invested an afternoon, and turned out you can say, hey, GitHub, get all of the push times for this repo. And you get back some ugly JSON structure, and you hit it with a stick, and you get out a bunch of times and commit strings. And the output of this is a LaTeX table. Exactly the sort of thing you might paste into a report you're writing to your university honor council. So now that's just an off-the-shelf tool for me. Lots of fun. Here's another simple tool, and there's 4 other people who have similar tools that do similar things. You don't have to use mine, use somebody else's, I don't care. So it's often the case that you want to clone all 200 of your student repos all at once. So, okay, find everything that begins with com215-week05-trees, give me all of them. And this will go and get all the names, and then do a git clone 200 times, and you end up with 200 directories on your machine. Once you've got that, then little shell scripty stuff is your friend. Like all those Friday private tests, I do 200 clones with my tool, and then I write a little for each script with my shell. Copy the file to that, git add, git commit, git push. And it runs for 2 minutes, and then all of my students have an extra file in their repo. That's it. Moss plagiarism detection, git clone 200 repos. I don't want to have these huge long directories for Moss. Moss sometimes gets confused by that. So I manually copy the files up to the root that I care about for the plagiarism detector. Then I run Moss on everything /star.java, which will only match the ones I care about. So I'm a frequent flyer with our university's honor council. I've got this relatively well automated now. Travis CI is also a place where I built a tool. So as of 2 years ago, the way it worked was that Travis did not auto-activate a repo. Activation was you flip a switch that says, whenever a commit happens on that repo, go and run it on the Travis server. So it used to be that I had this script that ran once an hour that said, hey, Travis, enumerate every repo, activate them all. And that was just a cron job running on my desktop Mac in my office. So once an hour, it would say, hey, Travis, activate everything. Today, Travis auto-activates automatically. So maybe you don't need this tool, but I kept it running anyway. And for 1 week in the fall, for some unknown reason, it activated like half my class's repos. So Travis, something happened mid-semester in 1 week, and my tool cleaned it up behind my back, and the students never knew. So is that going to happen to you? I don't know. Welcome to the world of distributed systems, right? So this is handy to have as a backup, even if you never need it. Briefly, I hacked all these tools up in Python. There's a great library called requests. If what you want to do is talk to some JSON RESTful web API, the requests library for Python makes it super easy. And once you learn it, then if you have one of those moments of panic. So here's a moment of panic I had. I forgot to check the box on GitHub Classroom that said, make all the student repos private. Then I'm 30 students in, and I realize that 30 of my students have already cloned it and have world-readable public repos. Eek, right? Well, I took my clone all part and got rid of the cloning part, and instead figured out the API call that says, make it private, please. So 30 minutes in a white heat of panic, and then I solved my problem. So if you have a similar white heat of panic, you might find that these tools are hackable to solve your problem. Your mileage may vary. I'm in the middle of building a new auto grader because everybody, kind of like Jedis have to build their own lightsaber. I'm building my own auto grader. I love what Geoff Chalin built, but the problem is you have to write these XPath descriptors to dig deep into XML to query things, which means that you write tests, you test it, it didn't quite work, you write it again. Debugging your test script sucks. So my goal is to be able to dump annotations into my Java that say, this unit test is worth 4 points, this unit test is worth 4 points, and getting coverage is worth 1 point, and blah, blah, blah. I just want to stuff this in my Java once and have a tool that extracts it. I'm halfway there. If this is interesting to you, if you want to join in and help me finish this and be a guinea pig, contact me afterwards. I'm looking for guinea pigs. All right, almost done here. So miscellaneous things. Travis CI today will give any of you one concurrent build for free. One concurrent build is great up until 5 minutes before the deadline. So on my personal computer, doing a build and running all the unit tests from scratch, maybe 15, 20 seconds. On Travis, 3 minutes. And probably 2 of those 3 minutes is setup and teardown because inefficiency of Travis. Well, if 200 students all do a push 5 minutes before, then we're now 600 minutes behind. So we're talking about, in the worst case, the student might be 3 hours from push to verification by the CI server. And that's not really acceptable. I even had students say, wow, it didn't work fast enough, so I committed again just to try to press no, stop. So anyway, Travis will give you Travis CI Enterprise, which is to say run it on your own hardware for free. I've asked, hey, Rice IT, will you install this for me, please? Crickets. We'll see. Separately, they were really nice to me, and they gave me in the fall like 45-way concurrency because they wanted to gather data on it, and I have no idea if they're ever going to roll that out. They haven't. I'm like, do you have something I can talk about when I'm in front of all these people? And they gave me back many words signifying nothing. So I don't know what their plans are. Another best practice is make sure you have a separate GitHub organization. So, class name fall 2018, class name spring 2019. Change the name every year, so that way you don't have like new student work and old student work mangled together. Keep them separate. In particular, because then what you want to do is have all of your graders, labbies, TAs be owners of the entire organization. So the way that you can contain that from them being able to see everything ever is have it be one per semester. And then for your, for the repo where I maintain all those 18 branches, that's in a completely separate project that no student, grader, labbie, TA has any access to. That way I have granular access control to my resources, and for all the student submissions, all of my graders can get at them without any friction. Anyway, stuff happens. I had one kid who for some reason changed his GitHub ID halfway through the semester. And that broke a separate script that I had to match things up with things. Not every student did every assignment. I have a forgiveness thing where I'll drop your lowest grade. And people would take advantage of that. And so that meant that I had, assigning what was there to the graders as opposed to taking the names and assigning them to the graders, that was important because any given week, some number of students would deliberately choose not to do it. So that my grading script only assigns what's there. It doesn't assign what's not there. I have a survey at the start to collect bunches of data. I'm sure you all do too. Make sure that you have some independent way of mapping from your university email addresses to student ID numbers to GitHub names. Because students will choose their own GitHub names, and turns out they aren't fixed. They can change them whenever they want. So anyway, it works. So handful of acknowledgments. I have a co-instructor, Zoran Budimlich. He was immensely helpful, and he shares the credit. Everything that I did started with this other guy, Omar Sheikh at San Francisco State. He wrote it all up, and I just copied what he did and then took it from there. So he was immensely helpful, and I hope you copy what I did and take it from here. Vanessa is the GitHub consigliere. She's amazing. Whenever I have a GitHub problem, whenever I'm I do this and it breaks and it shouldn't break, help. She has connected me to all the internal engineers, and they've been able to repro my problems, and I know that they are working on it, which I wish I could say for some other services online. Anna Nagy has since left Travis CI, and she was my contact there, so I no longer have similar inside access to Travis. But Travis, at least a year ago, was really interested in working to help. I don't have any visibility into what they're doing today. I'm really curious. And props to Joff Chalin, who showed that you could build this great autograder, and now I'm trying to build an even greater autograder. All right, and for those of you who came in late, all these slides, the PDF is online, so you can download them. All the hyperlinks are clickable and get everything you need. All right, thank you very much.
Thanks, Dan. Yes, all the slides from today will not only will we share them on Twitter under the SIGCSE hashtag, but you'll get them in a follow-up email from me. So do not despair. Next up, we have thinking. We have Paul. I pull up my notes here on Paul. At GitHub Education, we have this teacher training program called Campus Advisors. And as part of the certification process for Campus Advisors, I take a one-on-one phone call with each of them to talk about their experience. I like to know about their course design, what their students are like, and their specific challenges. These campus advisors have completed about 10 hours of teacher training on Git and GitHub, and then they serve as a resource for other teachers in their school. So they become the Git expert that everyone goes to in their department. The spring, we welcomed the first class of campus advisors from around the world, and Paul was one of those. And when Paul and I had our certification conversation, he told me about this project he was working on to generate problems so he could focus on practice and feedback at scale. And I was like, more people need to know about this. So I'm so pleased that he is here to share it with you. Paul is an assistant professor in the computer science department at California State Fullerton. He received his PhD in information science and technology from Osaka University, and he completed his postdoctoral research at Carnegie Mellon. Currently, he uses data-driven discovery, creation, and implementation of design patterns to improve tutoring systems. Please welcome Paul.
Thanks for the kind introduction. All right, so this afternoon, I'd like to share with you sort of an offshoot. I just started teaching at Cal State about 2 years ago. I immediately got assigned to an introductory programming course because many instructors didn't want to, I guess. But anyway, my research was really into looking at programming. Students were starting off with programming, and so I felt, ooh, free data. So I took on the job. And the biggest issue that I had really was handling the amount of work that was required for that course. And this project is sort of an offshoot for that. Basically, the idea here is we wanted to create sort of like a repository of programming problems. And we happen to be using GitHub because it's a great tool for doing that. And the goal here is to come up with a repository of programming problems that not only me or my colleagues can use, but hopefully get other instructors involved so that we could leverage on each other's work to help create, check, and give feedback on programming problems, specifically in a classroom setting. So this is a brief outline of what I'll be talking about. I'll talk about the introductory programming course and its challenges that I've at least seen in the past 2 years I've been teaching it. And talk a bit about effective practice, which I felt addressed some of these challenges. A case study, what we've been trying to do at Fullerton to apply some of these practices. And then this is where we found some issues and gave birth to this programming problem repository. And then I'll give you a short demo of how it would work, and then where we go from there. So just a brief background, at Cal State Fullerton, we have 3 required courses for students to take. When they come in, they need to take a 120, a CPSE 120, that's the introduction to programming. That's where you have mostly about loops, conditions, and things like that. 121, you have more of the object-oriented programming, and this is actually the course that I'm teaching. So I'm in the second course, and then there's another course that follows that, which is data structures and algorithms. And so I'm going to talk a bit about the challenges that I often see, and let me know if that's something that you guys see as well. The first is the difference between concept and implementation. When you talk about the concept, it seems that students are able to get it. When you talk about loops, they understand the concept of repetition. When you talk about conditions and all that, they seem to understand. If you give them tracing problems, they're able to get it. If you ask them multiple choice questions, they're able to get it. But suddenly when you change it, can you create a program from scratch? This is now from concept to actual implementation. They really just don't know what to do. There seems to be a gap there. There's a problem there. So that's one of the big issues that we have. Second, it's a totally different skill, I think. Learning how to program, how to write a program is one thing, but actually interpreting and deciphering what the compiler is telling you is a totally different skill. And we're using C++, by the way, and it's, I guess, one of the most kind of hard to decipher type of warnings and errors that you get. So in this case, it's telling you about expected initializer before int when it's actually just saying you're missing a semicolon. So we have used G++ before. We recently just switched to Clang++, CLang++, which has a better kind of error messages, and it's been pretty effective. We've started using it this semester, so at least you get rid of this. But still, the point is, it's a different skill, understanding what the error is and trying to track back where that is in your code. Worse is, of course, your logical errors. Like this is probably the most common errors that students make. Why is it that my output is different? And it's pretty hard to track down where that is, right, for a student. For us, yes, we know that, but for students, it's really tough to do that. Then, at least in our student population, what's interesting to see is that there's a huge gap in background knowledge. So if you're going to see to the right, we have like this peak to the left, and then there's a peak to the right. The left, these are really the students who are doing pretty well in class. This is the midterm grades, by the way. I took it from the last semester. And then over the other side, you have another peak, which is the students who are more or less doing well, up to some students who are kind of like struggling. So really, there's a problem here because, you know, if you cater to the students who are doing well, you leave students behind. If you cater to the students who are kind of like struggling a bit more, then you're kind of getting those students who are really advanced a bit bored. So how do you navigate around that space? So that's a big problem. And what we've been exploring is looking at effective practice. And I think, you know, we've heard of the term before, practice makes perfect. And so that's sort of the model that we've been trying to apply here. So when we talk about practice, of course, we know that practice needs repetition. You need to refine the skill by keeping, doing it over and over and over again. But it's not just about repetition. There's also that concept of, there's the spacing effect, or a spaced practice. This idea of forgetting and then recalling causes this generative processing and actually helps improve that retention. So you don't want to just give the same thing over and over and over again. You want to kind of change things up a bit so that they learn more and retain the information more. Then you also need appropriate feedback. You can't just say, your program is wrong, move on to the next one. You do need to describe, why it's wrong. Otherwise, they don't know what to do. So you want to give you want to describe what the misconception is, try to help them through that, and then hopefully when they get it, that reinforces that correct information. Hopefully you don't introduce new misconceptions and give correct information instead, and that's what you're trying to reinforce. And then finally, appropriate content. You don't want, again, this goes back to the last slide, the previous slide I showed with the 2 peaks. You don't want those students who are really good to keep on seeing the same content over and over again. Otherwise, they're just going to get bored. And although there are some research that say over practice might be good, or there's no really, there's no difference between over practicing and not. But I think, given the amount of time that we have with our students, with our limited kind of time with you in a 1 hour, they probably can just give you 20 minutes. The rest, they're doing something else. You do want to maximize that time. So I think it's better spent on learning something new. So you want to make sure that the content that each student gets is more or less at the same level as what they're working on. And so we're applying this practice in the course CPSC 121. Like I said, this is an object-oriented programming course. This is taught on C++. And the idea is to actually have a lot of practice within 14 lab sessions, which are around two hours every week. We have a 16-week semester, and then for each lab session, we're assigning one topic for each of those lab sessions. And this is just sort of a run-through of the different topics that we're covering. We start from basic I/O, conditions and loops, all the way down to templates and SDL. So, to apply practice, we felt that, let's start with 3 programming problems. And it turns out that 2 hours, more or less, is enough for students to work on those 3 programming problems. The advanced students sometimes are able to do more than the 3. Majority do 3. Others, unfortunately, can do 1 or barely do 1. But we thought that 3, 3 is a magic number for everything. So 3 seems like a good number. Let's start with 3 programming problems. So it's one thing to think about implementing something. It's different when you're actually doing it, the technical aspects. So if we were to create 3 problems for each of the 14 topics, that's going to be 42 different problems. That doesn't seem too challenging because I've probably given a problem before. I can reuse something. There's something in the textbook. I'm going to grab that. There's something online. I'm going to grab it. So 42 problems is doable. How about grading, though? I teach 30 students. If you were to look at 30 students in one section, that's 42 problems times the 30 students. That's 1,260 solutions. That's pretty hard to do. I think we're too busy to do that manually. That's kind of hard. I teach 60 students, so that's 2,520 solutions that I need to check. I'm lucky because I have a grant right now, and that's why I only teach 2 sections. But I'm actually supposed to teach 4 sections, and that's 5,040 solutions. So effective practice, do you really want to do that then if this is the amount of work that you want to do? Probably not. Okay. But wait, there's more. There's feedback, right? We talked about feedback. So you're not just checking the solution, you want to give feedback on that solution. So that's 5,040 potentially unique solutions that you have to give feedback for. And you don't only give feedback once because, oh, you fixed this one, and they do, and there's still a bug, so you have to give feedback again. So imagine how many times you're going to check solutions every time over and over and over again. That's just too much work. So basically, I felt misery loves company. I don't want to do this on my own. I know everyone has a similar issue. Why don't we attack this problem together? Let's solve this problem together. And that's basically one of the major goals of this open repository of programming problems. Let's take advantage of the crowd. Let's crowdsource this. Let's reduce the effort in creating the programming problems. Instead of I have 42 problems. You have another 42. Voila, we have 84. And if we get more people involved, we can get more and more and more programming problems. Then, of course, as Dan said, professors are not perfect. So my programming problems that we had last semester had a lot of bugs. We found them. We fixed them. We're giving it again this time. Less bugs, less problems. That's just me. But if there were a bigger group of people, we can use each other's code and work on top of that, and we can all refine it. And we have not only just a repository of many programming problems, but actually good programming problems. Then this is the key aspect that really saved me. It's not just about creating the programming problems, but are there tools that we can use to help us do the checking automatically? Because we just cannot give feedback and check 5,000 different solutions. So I'm going to talk a bit about unit tests, linters, and code formatters. I'm not going to go into detail with that, and we can talk about that after. We're going to be in the booth, so if you have questions about that, I'd be happy to talk about them with you. But at least I'm going to talk about how these are useful in class. And finally, the reason why I'm here, thankfully, that's why I got to SIGCSE, because Vanessa learned about this. We are using GitHub and GitHub Classroom a lot for this project. And the reason why is because we just needed something that is accessible. If we want to make a project that is available to a lot of people, why not choose a company like GitHub who can actually help us distribute that? And it's perfect because we do need a lot of the versioning. Version 1 version 1 of the programming problem is not so good, so we need another version and improve on it, and we all collaborate to work on that. Warning, this is still in development, so what you think seems to be perfect is actually not. That is a work in development, and that's exactly the reason why I'm talking here in front of you, because I'm looking for people who would want to work with us to work together instead of kind of just do our own separate thing. So do keep that in mind. So this is basically the repository. Right now we have 146 programming problems in there. It's not a lot, but that was at least our goal. I had 3 students who worked with me every week. We need to get 10. We need to get 10. And so this is actually all of their work. We got 146 different programming problems. And this is an organization. The way we structure it is we have a GitHub organization, and under that organization, each repository is basically the programming problem. And just to zoom in how it looks like, this first one, if you click on that, you're going to see this repository for the draw triangle. And this basically contains all that files. It has a short description of what that project is or what that problem is. It's about writing drawing a triangle using asterisks. There's some tags that we've been kind of playing around with. And then more importantly, there is a problem and a solution folder. Sorry, I don't think it's that readable. But again, the slides are going to be available so you can see the screenshots more, or even better, we can talk about it after the talk. So the problem folder is basically going to contain the problems that you're going to be sharing to the students. The solution is simply the solution to that problem. And if you dig deeper, going into the problem, this is actually what the students are going to be seeing when they start using the exercises in class. The important part here is it has sort of the README. That's where the description of what the problem is. So here it talks about the draw triangle problem that asks the student to write a function called create triangle that will take in some inputs, and this is the expected output. Then you have also the test folder. This is then where you will have your unit tests. Again, I won't talk about this in detail. I can share with you, but basically this is what's responsible for doing all the unit tests, the linters and the checkers. Format checkers, I mean. Then the solution folder, as expected, is really just the files that you would use as an instructor if you wanted to check. Say, I'm going to get a problem. I want to get an idea. How does this look like? I can actually see the source code of someone else's solution for it. Not probably, whoever has submitted that problem. Okay. So now that you have an idea what the repository is like, the next step would be, again, it's more like you being a consumer if you're teaching it, so you don't have to create your own problems. You can actually just look for the problems and reuse them in your class and then distribute them in class. So there's different ways for you to find the problems in the GitHub. So GitHub has its own search functionality. That's great. We're also coming up with our own. It's more like a tag-based type of search. It's using the tags that we had inside of the README, basically. But anyway, this is something we're still working on that allows you to say, imagine you are teaching a course, maybe also an introductory programming course. You want to look for a problem that has something to do with loops. Then you basically just see all those programming problems that match that tag. And then when you click on them, you're then going to see the exact same repository. This is really just a search functionality that we're playing around with. So the point is you just need to find the problem that you want to use in your class. Once you find that, then you just create the lab exercise. How would that look like? So if you found the lab exercise, you go to that repository that you want to use. So on GitHub, I'm assuming that people are at least familiar with the workflow, but basically you're going to click clone or download on the page, on the repository page of that problem. Then you can do git clone, and then you get the URL, and then you're basically going to download that programming problem. In our case, we have 3 programming problems. So what we do is I basically clone 3 different repositories, and then I'm going to grab whatever is inside of the problem folder, put that in another folder. So basically, I'm collecting all the problems that I want to use for the exercise. And then I'm going to create a new repository. So this is now my class repository. A while ago, I was talking about the repository of the programming problems. Now, if you're going to create, assign this lab exercise to your class, and you have, like what Dan said, you would create an organization for your class. And then you're going to create a new repository, which is sort of like your starter code. So the idea is you picked up all of these problems that you want to use in class. Then you create the starter code. So this starter code is now going to contain all the problems that you have selected. So this is for the draw triangle, another one for the draw rectangle, another one for something else. You put that in that repository, push it back onto GitHub, and what happens is you now have your starting code, and this is what you're going to be distributing in class. So as far as the instructor is concerned, this is it. That's what you need to do. You're done. You have your lab exercise. How do you then distribute it to the students? This is where GitHub Classroom comes in. And again, this is a pretty very straightforward process. You can apply for a GitHub Classroom. Again, it's free. You just create a classroom. In my case, this is my classroom. Inside of the classroom, you create an assignment. And when you create the assignment, you just specify, is it an individual or a group assignment? You've heard about Dan and the headless states, so I just do individual assignment. This is, a lot of them are like first-year students, first time they've seen this, so we're just avoiding as much of the extra load, so we just keep it simple. We go for individual assignments. And then the key part here is that when you create an assignment, you can specify the starter code. So this starter code is the one that you just pushed. So again, the process would be select problems, put them in a folder, push them to a starter repository, and then link to that on your GitHub Classroom assignment. And once you're done, that's it. This is the link that you then provide to the students. So it can be on your LMS, it can be a message, it can be like a PDF handout, just like what Dan did. But the point is, that's it. You don't have to create your own problems anymore. So that's the vision. Okay, so lab exercises in action. So what do the students do? Then the students just click on the link. I usually put in like the roster of my class so that it would be able to link their GitHub accounts with their email addresses in school. That's a good way for me to at least track the students and look for them. Because again, you have email addresses and GitHub names that kind of like who's this person? I don't know. And so it's hard to track. So the roster is pretty useful for that. And then when the student accepts the assignment, again, just like Dan said, it's going to clone your starter code that you built. And then the students are going to have access to their own repository, which now will contain all the starter code that you have created previously. So this is now then how it looks like. If you notice, these are like the 2 folders that I have created that would basically contain the draw triangle and the draw rectangle problem. So let me just insert this a bit, because this might change how things work with other people. Again, this is C++. And the unit tests that we have created are specifically for C++. And it was, we always had that issue where but it works in my computer at home, those kinds of things. So what we ended up doing was, hey, let's hit two birds with one stone. We felt that let's introduce a new operating system. Let's introduce them to Linux. So we created Tuffix, which is really just Xubuntu with a changed wallpaper and packages. And Tuffix is just a name because the school mascot is Tuffy the Titan, so we called it Tuffix. And the idea here now is we distribute them as a virtual machine, so then no one has an excuse. You just have a virtual machine, run it on your computer. Whatever you can do in the lab is the exact same thing that you should be able to do at home. So it's been pretty successful, and at the same time, they then learn how to use the command line. They learn how to use Git. I also have like a very short tutorial. 1 week is enough to teach them. They get used to it pretty quickly. Like by the 3rd week, everyone knows how to add, commit, and push. And surprisingly, they're able to memorize clang ++-stdc17 main.cpp-o main. Repetition is very, very effective. I tell them, this is never going to be in any exam, but I bet by the end of the semester, you're going to memorize this one way or the other. So this is how Tuffix looks like. Again, changed wallpaper and packages. It's really just Xubuntu in the background. So going back, so you now have the students. How do we actually help the students? So this is something that can happen either in the lab or even at home, because again, GitHub makes it really easy for the students to work remotely also. So the idea is the students go to the same process. They click on the link when they accept the assignment. They have the repository. They can just get the URL and clone it, just like what I did. But this time, they have their own repositories where they have access to all the code. And then imagine that the student has already completed answering the problem. This is the student solution for the triangle problem, for example. They have solved the problem, and then this is where the unit test comes in. I know it's not visible, but use your imagination. Okay, so they would type in make test. We're actually just using a make file in here, and when they type in make test, it's just compiling the unit test. We're using Google Test for this. And then the great thing about this is now students get some kind of feedback. This is where the immediate feedback comes in. As an instructor, it's a lot of time savings. If I have 30 students in the class, instead of just like answering each student's question, is this right? Some of them don't even have the capacity yet to think about unit testing or what are the concept of what the correct input and what the correct output is. They don't have the concept of you need to test multiple different inputs to know that the output is correct. So the unit test is actually helping with that. It cuts down on the amount of questions that I'm asking as an instructor, and I can focus more on the higher level questions that are really harder to answer instead of like the extra 1 minute that you just spend on one student. 1 minute lost answering a simple question is actually a lot of time for students who are getting stuck trying to figure out a deeper question. We also have the concept of your linters. This is quite new and we found really interesting. A linter is sort of just looking at common bugs, errors, structural issues, best practices, and it's really just comparing the student code against that. So it's pretty hard to read, but there is a problem with the student's code wherein they forget to put open and close curly braces in the for loop, and that's usually an issue because they are intending to have 2 statements to implement in the block of code of the for loop, but then they forget it. Those are stuff that the linter is actually able to pick up. So it's actually telling the student, hey, it's actually good practice to put in curly braces whenever you have a loop or a code block, regardless if it's one statement or not. It also handles things like variable initialization. It handles things like the formatting or the indentation and things like that. So this is, again, another feedback that is pretty useful. I was surprised that it actually solved a lot of programming issues for my students. I didn't even have to look at the code. It's really just the style. Telling them to initialize their variables fixed a lot of errors for many students. The last one is also the format checking. This is more explicit. I know this comes free for many IDEs, but we felt that it was really good to introduce students to good, like a lot of best practices early on. So the format checker is really just forcing the students to take a look at how they organize their code indentation, spacing, and things like that. So this is an explicit way of doing this. This just runs in the command line, and students can check, oh, I missed a space here, I missed a space there. A lot of the students complained about this a lot. So what we're trying out this time is we're still going to give you the message, but here's a plugin that would automatically format the code for you. So we feel that, hey, we're cheating, but the point is they're aware of it. And you'd be surprised just seeing this again repetitively, they suddenly get that habit of indenting the code, because then when I do the format check, I don't have to go back to my IDE, click, clang, format, right? So it's still time saving. So it somehow works. So anyway, so that's it. And then the good thing is this also doubles with checking. Whatever you can do for giving feedback to the students is also related to checking. Now we're not only checking the correctness of code, but also the coding style, because you're looking at best practices, you're looking at indentation. So you've kind of automated the process of checking those stuff as well. So for submission, assuming that the student has finished the problem, it's pretty easy. Add, commit, push. They're done. That's it. And as an instructor, going back to your classroom, you have access to all the students' code. You can look at their number of commits to keep track of that. And you can even download the repositories. This is pretty new. Everyone had their own versions of downloading all of the code from GitHub. So obviously, GitHub is going to come up with their own solution. So now you can do that. But what we've been trying to do was also attempt auto-checking. I guess, I don't know if GitHub is ever going to do this, but a lot of instructors are creating their own versions of checkers and graders. The way we do it is not as graceful yet as what Dan has been doing and many other people have been doing, but more or less, this is sort of like the features that our checker is doing. One is obviously downloading all the repositories. 2, overwriting the unit tests to avoid cases of manipulated tests. Students are sneaky. Instead of actually generating the output, they change the unit test. So you want to make sure that you're overwriting it with the actual unit test. We delete and recompile the student programs just to make sure that their programs are actually recompiling. Otherwise, it's actually going to use the old version of the code. And then run the unit testers, the linters, and checkers, and we just dump all of the output into a text file. And this is what our graders are now using. So you would think that, are you really just dumping to the files? Like, isn't that going to be hard? I think the hard part is actually going through each of the 30, going in, compiling, checking the output every time. So what this does is really just automating that. So our graders are really just looking at this text file. We could do better. I can talk to Dan, and I'm interested to kind of like see how he does it. But that's basically the idea. And then I think the important part is, and it's not really talked about a lot, is how do you then translate that to grading? The way I do grading is, or at least my colleague has introduced this concept to me, is really creating a rubric. And because this is a lab exercise, what's important to us is, did the student actually do the work? That's what's important, not really correctness specifically, but are they doing the work? Are they practicing? And so if you look at the rubric, let me just say it because it's hard to read. There's one rubric that's on mastery that really just says, are you able to understand the concept or the topic? So out of the 14, how much did you know it? There's 3 programming problems. So what we do is just check, did they pass all the unit tests for problem 1, for problem 2, for problem 3? If they did, then they've mastered it. If they have not, maybe they require more practice. If they just started, maybe that is just started the exercise, or they did not submit anything. This is the unit test output. Code formatting, just looking at indentation, the style, this is your format check. Your coding style, are you following best practices? This is your style checker, your linter. So 3 out of the 4 things that we're checking is already semi-automated. The graders don't even have to manually check the code. These are all outputs from the automated tools. What we have not found yet, though, is documentation. But basically, the good thing is students just need to browse the code. They don't have to inspect it very deeply. Probably they might watch out for like brute force solutions and things like that. Hopefully the unit test catches them. But I do encourage the graders to at least look at the code, and this becomes like a pretty easy job for everyone to do. So some insights from using this for the past 2 years. It was great to actually make the lab exercises a bit more self-directed. So the way I run it is I don't ask for the students to turn in the exercise on the same day. I actually kind of spread it. I used to say at the end of the finals, but students, they're always going to submit at the last moment. So now I have like a milestone on the midterms. So we have 14 lab exercises. So for 1 to 7, they have to submit that by the midterms, and then everything else by the end of by the finals. And it's pretty effective because now you have students who are working at different paces. Students are really good. They can just keep progressing. Many of them finish the lab exercise or maybe 2 in one setting. The others who are kind of falling behind, it takes them maybe 2 or 3 weeks, but then everyone is moving at the same pace. Those students are moving really fast. They don't have to wait for the rest of the class, and that's really effective. You have faster turnaround time because I asked them to submit by the midterms. If they submit the answer and I just check the unit test, if it fails the unit test, please redo that. So they can keep on resubmitting and you don't have to really go through the code even. Just look at the unit test. Then at the midterms, when everything is due, then that's the time that you can go in and look at the code and maybe give partial points or something like that. Instructor availability is great because now, again, I don't have to bother with the very low-level issues. I can accommodate more questions in the lab or even offline because the questions tend to be more higher level. And then effective practice, sort of just like a checklist. Did we do what we set out to do? Yes, appropriate content because not everyone had to answer at the same pace. They can go at their own pace. And no one had to wait for anyone else. Frequent practice, I think 42 problems, that's pretty frequent, I think. Spaced practice, I haven't been able to think too much about this, but this is, again, when we have a lot of problems. Now you can start mindfully selecting which problems you're going to ask. So if, say, you see that a lot of your students are really struggling with conditional statements, look for problems that also use conditional statements. Even if you're talking about functions, even if you're talking about files, because you want them to have spaced practice on conditional statements, then select those problems. It's easy to select those problems using the repository. Finally, appropriate feedback. Again, you have the output from the unit tests and also from the instructors. Because of the time savings, it's actually easier now to give students immediate and more useful and appropriate feedback. Future work, again, like I said, this is work that I want to do with people. We want to crowdsource this, so please, if you're interested, talk to me. I'd love to hear your thoughts. This is not the perfect solution, I know, and you have great ideas, and I would love to have them and learn about them and see how we can incorporate that into the system. It is C++ only, but again, if we have crowdsourcing, we have set up everything, we can always support other programming languages. At the end of the day, a programming problem on sorting is the same, regardless if it's Java or Python or C++ or whatever. So you have the same problem, but maybe you have different unit tests and different tools that you're using for a different programming language. Variations, you might not like the way I write them. You might not like how it is displayed. Maybe you can fork a programming problem and then have a different variation. So those are, again, things that we could do together. Streamlining the process, there were a couple of steps. They're not too bad, but if we can streamline everything, that would be great. That is a project that we're currently doing right now. And I just wanted to give thanks to the different faculty and students who have been contributing that I fooled into helping me out with this project. Thank you. That's my email address. I'll also be at the booth with Vanessa, so if you have questions, please feel free to visit us. Thank you.
Hi. So the quick follow-up at the booth, we're doing sessions every hour on different topics that were listed here, individual work, group work. Tomorrow in this room at 3:45, Dr. David Malin of CS50 will be going through some of his tools, his custom tools. And if you have questions for these folks, they're going directly down to the booth. Please meet them there. They will work with you on your specific use case and see how to collaborate. Thank you all for coming. Thank you. Thank our speakers.